Welcome to lecture 7 of chapter 2. Today we're going to talk about alkalinity, and this is aligned with the last two lectures when we started talking about titration first, and then it was about buffers, and now it's about alkalinity. And as you'll see, this is heavily connected to the last two lectures. So long story short, alkalinity is kind of buffer capacity, but for a specific kind of system and pH range. So today we're going to start with describing alkalinity in environmental system, why it's important, and then quantify alkalinity, and then use alkalinity to estimate the solution pH of a mixture. So very useful, and alkalinity in general is a very useful concept that you see here and there. Sometimes with the same meaning, or sometimes they are like different approaches of alkalinity. And then the other term that normally people use is acidity, which would be the opposite of this, opposite of what we were talking about. So the focus would be basically all on alkalinity today. So we started with acid-base, and then we moved to titration as an analytical method. We mentioned that this is basically a very useful technique to look at the change in pH as a function of acid or base we're adding. And then we compared this to sort of a pure water system. So then if we add sort of a weak acid, then we saw a deviation, or a weak base. We had a deviation or sort of a delay in terms of change in pH. And then later we talked about also buffer capacity, and combined together we were able to gain important information from the system. For example, how much total acidity we have, how much or what's the pKa of potential acid we have, and also in the last lecture we talked about the buffer intensity of the system. So we defined this to be sort of a buffer intensity. Which was the resistance for pH change when we were adding a secondary solution, which in that case was just a strong acid or base added to the solution through the titration experiment. So as I mentioned in the first lecture of titration is basically all about mixing. So you have something that is known adding to something that is unknown. And we specifically focus on titration because we were interested to see how the system is reacting when it comes to adding strong acid or base. But the same concept can be applied into any mixing in environmental system. For example, if you have a wastewater going to a river, so it's basically the same concept. So here we're introducing alkalinity to be able to eventually talk about what happens to the mixture when the mixing happens. So as I mentioned, this could be mixing with any water. So titration was just a specific example. And in many systems, many practical systems out there, when it comes to wastewater, introducing to a river, for example, most of wastewater is acidic. So we normally deal with introducing an acidic solution to a receiving water, which could be, for example, a river. And what we're interested to know, obviously, is when we introduce this wastewater into that river, what would be the pH upon the mixing? So what would be the pH of this part of water? Because that information is very important, because then later we can say, whether we're within the safety threshold, for example, in terms of biodiversity of that specific region before it gets to re-equilibrium again. So what we're interested is to know, how does the pH changes? And we answered this kind of question through the last two lectures. So this is kind of a titration experiment. So we're adding something that is known to something that is unknown, and we're interested to know more about what's going on here. So the difference between the previous case was this was a strong acid or strong base, but now this is a wastewater with some acidity. So that's one difference. So now let's specifically focus on alkalinity. So I want you to read this part, and then we're going to talk about that. So it seems up to here, alkalinity is kind of a buffer. So it's a buffer capacity or buffer intensity that we talked about in the previous lecture. But from here, we're making it more specific. So first is a kind of buffer capacity when it comes to adding acid. And then adding acid up to pH of 4.5. So before, in the titration, or when we defined buffer capacity, we didn't have a limit of acid, the lower end of pH. So it was just adding to some extent. But here, specifically, we're targeting pH of 4.5. So it sounds sort of random, pH 4.5, but there are two main reasons to make this value very practical in order to be able to define that as a threshold for alkalinity. So the first thing is, eventually we're interested to know more about what happens to the receiving water, to that river, when we introduce that acidic stream. So the first thing is the aquatic life, or biodiversity. Generally suffers at pH of lower than 5. So that's one of the main reasons we're interested to see how it would impact the receiving water up to pH of 4.5. But the second reason, which is the main reason, is that for most of the receiving water, practically speaking, is either a lake or it's a seawater. What's the main weak acid that presents in that water? So that means we're talking about a long-term equilibrium. What's the main one? What's that? So what's the main weak acid that presents? What is that? Sorry. Yeah, carbonic acid. So because as you'll see in the next lecture, that body of water is exposed to air. And one of the weak acid that you have in the air, acidic gas, is CO2. And then as you'll see in the next lecture, we have equilibrium. As a result, we have some carbonic acid eventually in water. So most of this body of water that we have, they have to some extent, some concentration of carbonic acid. And now what's the reason carbonic acid versus pH of 4.5? So, So why 4.5? So this is the buffer intensity curve of this green one that I'm drawing for carbonic acid. And as I mentioned, the peaks are related to pKa. So this is the first pKa, 6.3. This is the second one, which is 10.3. So as you see, roughly before 4.5, there's not the contribution of the buffer capacity of carbonic acid is gone. So basically, before that, there's not much in water to contribute to alkalinity or to that buffer intensity. So the second reason would be the main pH buffer. In natural water normally is carbonate. So basically what happens, as you'll see in the next lecture, is CO2 in the air. Then it would be absorbed by water. So eventually we have carbonic acid. And that beta value is very low at pH of less than 4.5. And you saw this also here, that 4.5. Before that, the contribution of that green line is almost zero. And because of these two reasons, alkalinity is the capacity to resist up to pH of 4.5. So the definition is very simple. How much acid we need to add to that sample? Could be from seawater, it could be from any water or any solution in the lab to bring down to a pH of 4.5. So it's basically a titration kind of experiment. So to do a quick practice, if we have this titration curve, which we had in the titration lecture, so we have, this is the sample. This is for pure water as a reference point. So, and the initial pH is 6.8 basically. What's the buffer, what's the alkalinity of this sample? We're adding acid and we're changing the pH or lowering the pH. What's the alkalinity? What do you say, Shia? So we have to bring the pH down to 4.5, right? So that means we have to go from the initial point, which is here, all the way to 4.5, which is here. So we have to go up to here. And how much acid we added is basically the alkalinity, right? So the threshold was 4.5. So we trace this one. And this is how much we add, how much acid we have, or we add, to bring the pH down to alkalinity point, or the threshold. And in this case, the alkalinity is basically 2 milliequivalent per liter. So qualitatively speaking, it's very straightforward. You have a sample with some pH, more than 4.5 normally. Let's say a river, 7.9. And then how much acid you need to add to bring down the pH from that 7.9, let's say, to 4.55. So this is the threshold of alkalinity. And how much you add it is basically equal to the amount of alkalinity in that, or the acid resistant, acid neutralizing resistant capacity, which is alkalinity. So again, it's a kind of buffer capacity, but for a specific case. But as you see, this is very important when it comes to mixing. So now a little bit of a qualitative description on what contributes to alkalinity. For example, what if we have specific type of species, whether it impacts alkalinity or not, and if it does, how, increasing or decreasing, basically. So let's say we have a conjugate base of a weak acid, let's say bicarbonate, in that water. Does it impact alkalinity? So if you have more bicarbonate, generally speaking, can you say you have more alkalinity or less? So alkalinity was again how much pH would change if you add H+. So it does change, because into this system, if you add H+, then it would be converted to HCO3-. So H+ is consumed without observation in pH. And this would again add one more to bicarbonate. And then the pKa here is 10.3. And here is 6.3. So it seems this one overall, it contributes to alkalinity, and more you have, basically more alkalinity. So can we say any kind of weak acid contributes to alkalinity? That would be for sure one of the questions in the exam. Any weak acid? So let's put it this way. Any weak acid contributes to increasing the buffer capacity based on the previous lecture. They would eventually consume some proton. But let's frame it again. Any weak acid contributes to alkalinity. Would it be the case also? The answer is no, but why? What was the difference between alkalinity and buffer? That we care up to a pH of 4.5. So any weak acid, as long as pKa is bigger than 4.5, they contribute. So in the first lecture of acid base, we mentioned that weak acid, the pKa is bigger than 2, and all of them contributes to buffer intensity or buffer capacity, but only those bigger than 4.5 of pKa would contribute to buffer capacity. Because the protonation of those with lower than 4.5 and bigger than 2, it really doesn't matter, because we're not going to that region to be able to calculate for alkalinity. So the threshold of 4.5, it almost includes all the weak acids. So some of the example we had, the lowest was 4.7, I think, for acidic acid, and the rest was like ammonia 9 point something, carbonic acid like 6.3 and 10.3. So it does contribute. So the second one is basically the presence of a conjugate base of strong acid, SO4 2-. If we have a sulfate anion, does it impact alkalinity? Hypothetically, if what's that? So it doesn't. So it could consume proton to convert to HSO4 minus and add one more proton to form sulfuric acid. But when we look at the pKa, this is basically 2. The pKa of this one is minus 2. So it does not contribute. So if you're making a solution in the lab which has, let's say, sodium sulfate, when you're adding sodium sulfate, the alkalinity doesn't change. But if you add sodium carbonate, then you're adding alkalinity to the system. So that's the delicate difference between the two. So if you're adding the salt of a conjugate base, as I mentioned, this would also impact. So sodium bicarbonate, for example, we know this will be dissociated to sodium plus bicarbonate. And then bicarbonate can form carbonic acid. And the pKa for this one is also 6.3, so it does contribute. And it increases the alkalinity. So more of sodium sulfate you have, the bigger impact on the alkalinity. How about a strong acid? So let's say you add HCl. Does it impact alkalinity? Anyone? For sure, it shifts the pH, right? Or it neutralizes some of those weak acids. So it's helping you to get to 4.5 sooner. So it's basically impacting the initial alkalinity. So it directly impacts to alkalinity. What's the contribution? Is it increasing or decreasing? More decreasing. So basically more of HCl, less of alkalinity. And the last one is basically adding a salt. So NaCl is Na plus Cl minus. And as you can guess, this is also does not impact. So this is more on the qualitative description of what could impact. And now what we're looking for in the next part is making sort of a qualitative description of alkalinity as we did for buffer capacity. So if you remember for buffer capacity, it was a function of pH and the total acidity or the total concentration of weak acid. And we had this sort of alpha 1, alpha 2, the total plus some terms related to water. And we're expecting to see something here also because they share a lot of similarities, alkalinity and also buffer capacity. So we're expecting to eventually see something alpha, also to see total, and also to see the concentration of hydroxide and proton, which is the contribution of alkalinity of water. So the qualitative is what we talked about in the previous page. So now let's look at a random natural water. So that is out there. Like any other aquatic sample, it follows the charge neutrality rule. The very first lecture, we talked about one of the big assumptions in this course is the charge neutrality assumption. So let's say we have all the cations. Obviously, we have H+. Some of the common salt that you can find in water is sodium, potassium, calcium. But calcium is a divalent charge. So basically, we have to implement this times 2. Again, this is all about the charge balance, not mass balance. Also magnesium. And plus other cations. And obviously this would be equal to all the negatively charged ions. So hydroxide, then Cl minus, sulfate, plus all the bicarbonate and carbonate, plus other anions. So that's always the case for any sample of water. Positively charged, considering the concentration and also the charge, the Z factor, is equal to the negatively charged. And we just mentioned some of the very common salts that we have. So now we want to use the same analogy as we used for titration. So we introduced the Ca and Cb terms. So Ca was the amount of acid that we were adding, and Cb was the amount of base we were adding. And if you remember, when we were adding, let's say, sodium hydroxide as a base, that Cb term was equal to the amount of sodium that was in the system at any time. And also similarly, Cl was the amount of Ca that we were introducing in the form of HCl. So we could combine all of them and hypothetically say we added all of this strong base to the system. We added calcium hydroxide, sodium hydroxide, and all of them. So we can call this how much that Cb was that we hypothetically added to that body of water, or that exists eventually in the body of water. And similarly, we could say the same thing about these two. Why these two? Because they're the conjugate base of strong acid. Because sulfuric acid is strong acid. HCl is also a strong acid. But bicarbonate, let's say sodium bicarbonate, is not strong acid. So basically these two represent that Ca. It fully dissociates, and then we can consider these two. And here would be all of them. So now we can rearrange the charge balance equation. So basically simplify it in a form that, and also assuming they are not other cations or anions, because that would be, these are the major components. So you might have some, let's say, lithium or some other ions, but this is basically the major ones. So then we can say H plus Cb is equal to OH minus plus Ca plus HCO3 plus 2 CO3 2 minus. And also we're assuming no other weak acids. So for example, we don't have any phosphate, but in reality, we have phosphate in the system. So for the sake of simplicity, we're looking at only having carbonate in the system. So rearranging this a little bit, so it would be Cb minus Ca equal to bicarbonate plus 2 carbonate plus hydroxide minus the proton. Instead of carbonate and bicarbonate, we know we can use alpha term, a pH dependent term. Also looking at the total concentration of carbonate, so that term is easier to play with. So if we do that, then we can convert bicarbonate to using alpha 1 times total concentration. Then it would be 2 alpha 2 total concentration. So the total goes outside of parentheses, plus So just converting using the alpha terminology to get rid of the individual species here and correlate everything to the total concentration. So up to here is all about the charge balance and a little bit of mass balance. So we haven't introduced alkalinity yet. But if you remember, based on the definition of alkalinity, alkalinity means, let's define this as alk, means eventually whatever combination of acid base we're adding to the system. So any combination, any net combination of C acid, C base, to take, sorry, this has to be combination of acid and base. So this would be opposite. So any acid we're adding to the system, some neutralized by base. So the net amount of acid we're adding to the system to bring the pH from the initial pH to the pH of 4.5. So that's the alkalinity definition. To add acid, some of it is neutralized by base that we hypothetically added to the system. So the net acid that is added to bring the pH from the initial to the pH of 4.5. That's the definition of alkalinity. And now we have this term basically here. Now we can play with it a little bit and bring that in order to do this sort of a semi-integral. So now we can define alkalinity term for the system to be alpha 1 plus 2 alpha 2. Sorry, this has to be all negative. And from pH of initial, because alpha term is pH dependent, so we have to have alpha at two different pH. pH of 4.5 times total. Total CO3 is not pH dependent. Hydroxide is pH dependent. And obviously H plus is also pH dependent. So what we did was, again, defining alkalinity based on what we talked about qualitatively before. Now we have the term for the net or equivalent hypothetical net acid that was added to that water. And then we have to add as much as bringing pH from initial to 4.5. Now we're bringing this term here. So the first term is obviously a pH dependent. Alpha is pH dependent. So this would be from here to here. This is a constant, and these two are pH dependent. So what we need to do is to calculate this term at pH of 4.5 minus that term at pH of initial, right? So that's basically how we do this, sort of a semi-integral. But to make it a little bit easier, we can look at the pH of 4.5, because that's the value we already know, and see what's the alpha value. So when we look at pH of 4.5, because that's one of the points, then when we do the math, alpha 0 is almost equal to 1. I mean, you can do the math. pKa 6.3, qualitatively speaking, below 2 units. Before pKa, it means 100 times more protonated. That means we have almost all of your carbonic acid in the form of, all of your carbonate species in the form of carbonic acid. Long story short, you can do the alpha calculation. It would be pretty straightforward. pH and Ka, the only two terms you need. Eventually you get alpha equal to 0, or equal to 1. But what does it mean to alpha 1 and 2 then? if alpha 0 is 1, what's the... So the combination of all the three alpha must be 1. So the other two are 0. Again, you can do the calculation and see that basically at that value is almost 0. So that basically makes this term at one of these two conditions equal to 0. The other one is also, relatively speaking, at H plus of 4.5 or pH of 4.5. Again, this is a relative term, and OH minus at pH of 4.5. They are relatively small compared to the initial pH. So you'll see that later. And compared to the contribution of carbonate at that initial pH. So it seems the alkalinity, so we have to do alkalinity at pH of 4.5 minus the alkalinity of initial. It seems the alkalinity of, pH of 4.5 is almost 0. So, and it makes sense. The alkalinity, we just push it to almost 0. So that's how one of the threshold of 4.5 was because of that. So when we solve it for this one, it would be just solving for one single point. So then the alkalinity would be alpha 1 plus 2 alpha 2 at the pH of initial times the total CO3 plus hydroxide at the pH of initial minus H plus at the pH of initial. So the minus is basically you have to have this guy minus this guy. So the minus is already gone. Yeah, that's a good point. I was initially, when I was putting this note together, I was also confused about that minus. So this is the term to calculate alkalinity. As we were expecting, is a function of pH. We expect to see some alpha term, some total concentration, and some initial pH. So this is exactly what we talked about in the previous page. Sodium chloride, for example, it doesn't impact this one. Qualitatively, we talked about that, and now here, quantitative, we don't see that contribution. For example, carbonic acid, it does, because it's basically contributing to this guy. And also HCl also contributes to this term. So, but specifically, this is a specific kind of alkalinity because we didn't include any other weak acid. We only assume we have carbonic acid in the system. So this is carbonate alkalinity. So you basically can do the same thing for phosphate alkalinity and other weak acids, but it would be pretty much the same, like the same procedure. The reason carbonate alkalinity is the most important one is because basically any body of water is exposed to CO2. And as you'll see in the next lecture, that exposure brings some carbonic acid to the system. And then we do the rest in terms of the speciation calculation. But when it comes to phosphoric acid, you don't have that gas in the atmosphere. So it's normally you don't have it in those, or it's not that significant as you'll see later. So it's a very straightforward kind of calculation to get to the alkalinity, which it seems is a very important features of that body of water. And later we'll see that we use alkalinity to predict the mixture, which is also very important. So now let's do a very quick, straightforward kind of calculation. So you guys look at this one. You have the initial pH of a sample, which is 8. Obviously, you have to add acid to bring it down to 4.5. So that amount of acid is equal to alkalinity. And then you know how much total carbonate you have in the system. So it's roughly 5 millimolar. And now you have the pKa. You want to estimate the alkalinity. So go ahead and solve for this one. I'm going to write down the alpha term just in case you need to use it, which you will. So this would be... So from now on, I'm going to remove that pH of initial from the equation because we don't really care about that 4.5, as you saw, is negligible. So that means when you have this equation, it's always about pH of initial, or in the initial state. So, okay, guys, you go ahead and so this is alpha 1 and alpha 2, again from the first lecture of acid base, or maybe the second lecture. And you have all the information. You just need to calculate this one, calculate this one. You're giving all of these three, and then you just need to insert it into this. Anyone calculated alpha 1? So this is roughly 976. And this is 0.05. Now you guys can calculate the alkalinity. Anyone with calculator? 4 point. Okay, I got 4.9. Yep, that is correct. So 4.9 10 to the minus 3 equivalent per liter, or molar in this case, or 4.9 milli equivalent, or 4.9 millimolar. So if you have this sample of water, if you add 4.9 millimolar of acid, then the pH would be 4.5. So now let's talk about the alkalinity when it comes to mixture. So this is something that we mentioned at the beginning of the lecture, that alkalinity can be used to predict the mixture. And that's probably one of the most useful part about alkalinity. So we're using this property of alkalinity, the fact that it's a conservative property. And that means if you have a so it's essentially a measure of water total buffering capacity, as I mentioned, to pH of 4.5. So we saw that as a contribution of buffer can be combined together. So in the previous lecture, water plus weak acid was the total. It can be the case also for alkalinity. So alkalinity of a mixture is basically a weighted average of the two. So that's how it works. As you saw in alkalinity equation, you had alkalinity, you had pH, and you had total. pH was a H plus and OH minus, obviously, and the total. So we're using this property of alkalinity to be able to eventually measure one of these three parameters for a mixture. So this might be a vague, but let's assume you have two rivers. You know what's the pH, you know what's the alkalinity, and you know what's the total acidity or total carbonic acid concentration of each. Then when you mix it together, let's say you're interested to know what's the pH of that. So that's a very important consideration, because you can later design or to understand what's the pH and then look at, for example, what's the danger to biodiversity of that specific region that you have the mixture. In the next lecture, you'll see that the pH you're calculating in this lecture is only at the time of the mixture. But later, when you leave it for some time, it will re-equilibrate with the air and the pH would change again. So if you have a mixing of wastewater and river here, the pH is different than, let's say, 2 miles down the river. So because between that 2 miles, you have re-equilibrium with the air. So it's, as you see, it's a completely different system. It's an open system. But at the mixture, we're basically using the three important fact with that easy, straightforward equation for alkalinity to be able to predict the pH. So alkalinity is a conservative feature. Total CO3 is also the same. So it's basically a mass balance or a conservation of mass, but the pH is not. So if you have a stream that has pH of 2, then you mix it with pH of 5, it's not, the pH is not 3.5. So That's a very practical way to approach it, actually. So we want to see if we mix this to a stream, what would be the pH. So now let's look at a very simple case. So if we have solution A, you mix this with solution B to get to, it's just a simple mixing, to get to solution C. And each, they have a pH value, they have a total CO3 value, and also they have alkalinity value for each. pH, you can use a pH probe, quickly measure that. Total CO3 and alkalinity, you can give it to Kara. She can do a titration. As we saw, based on the titration, we can actually look at the total CO3 and also the alkalinity titration, which is basically bring it down to 4.5. We can look at the alkalinity. So we did that for A and B. And now we want to predict what is it for C. So what is the volume for C? Not always, but for this class, yes. So VA plus VB. If you took, I guess, thermodynamics, you might have a delta V of mixture. It might not be 0. So it might expand or it might squeeze. But for this lecture, it's basically the same. So VA plus VB. So we are not ignoring delta V of mixing is equal to 0. So what about alkalinity then? What is alkalinity of C? Yeah, it is. The volume is a combination of the two. What about the alkalinity? Is it also a combination of the two? It's a weighted average. So this means Vc times alkalinity of C is equal to Va, alkalinity of A, plus Vb, alkalinity of B. It's the same thing for total CO3. So total CO3 might be a bit easier to comprehend. You have some concentration, so it's basically a concentration term in container A. So in terms of to get to the total moles, which is an absolute value, you have to multiply that by the volume. So let's say if 1 millimolar, but 1 liter, so then that would be 1 millimole in container A. So you have to basically multiply by the volume to get to the absolute, because we have a conservation of mass, which is related to the absolute of that. So in terms of, it would be milligram per liter, not mole, which would be the same because we're dealing with the same species. So it would be also Vc total C equal to Va total. So this would be not total of CO3 in C, total of CO3 in A, plus Vb total of CO3 in B. How about the pH? It's a very practical example, right? You have two mixture, let's say a Coke and a Diet Coke, and you mix it together. What's the pH of that mixture? So it's very practical. Can we do the same? Like, You can do the same weighted average. So basically equal amount of Coke and equal amount of something else. then they would be the average of the two. Something is missing, right? So you have a Coke. You have, let's say, something else with a different pH. Say the Coke is at pH of 5. Diet Coke is at pH of 8. And you have a random solution at pH of 8. So based on what we have here, if we add either of these two to the Coke, then the pH would be an average, or would be equal, would be similar for the two cases, right? Does it make sense? I mean, what's the base of this one? This is a mass balance eventually, like conservation of mass. This is a conservation of mass also. But here you're bringing a random mathematical operation, which is P, which is not necessarily related. So it's basically a minus log of something related to mass. So therefore, this is not equal. So you can't do that. Because of that, because pH is not a conservative, H plus concentration is, but pH is not. Because we did some weird mathematical operation on a mass term. We couldn't, but we have these two. Oh, sorry, we have these two, and we have a relationship between the three. So now we can predict the third one. So then, how to measure pH? It would be by using alkalinity term. So alkalinity of C is equal to alpha 1 plus alpha 2, 2 alpha 2. The total CO3 of C plus OH minus of C minus H plus of C. So basically this term is known. These are known based on what we have here. And these two are unknown. And we know how hydroxide is related to H+. So it's basically one equation, one unknown eventually. So that's why alkalinity, defining alkalinity could be a very good bridge in terms of doing the calculation eventually. For when it comes to the mixture, which is a very common scenario when it comes to environmental system, everyday life, you have it everywhere basically. When it comes to combining two liquids. Now you have this tool to be able to calculate for the pH. If it's unknown, calculate alkalinity or the total concentration of carbonic acid. So now we can do a quick example, basically mixing two rivers. River 1 has this pH, this alkalinity, and this total CO3. The same for river 2. But we want to calculate what is the pH immediately after mixing. So it might be a little bit weird because you have a pH for both rivers. But what we're looking for is basically when we combine the two. So here is river 1, let's say river 1 is going, river 2 is going. Now what's the river pH of the mixing? And now, again, as I mentioned, right now, we're just measuring the pH here at the mix. Later in the next lecture, we're gonna measure the pH here. But here, it comes all the way to absorption of CO2 on the way. But we don't want to talk about that. That was, I think, one of the questions for the exam last year. So, and this would be question 6 of the problem set also. So you have it immediately after mixing and also after equilibrium. So immediately after mixing, we don't need to be worried about the re-equilibrium or whatever happens after because of the presence of CO2 in the air. As we saw, the CO2, it dictates eventually the alkalinity. So we know, just approaching with V of mix, that VC is V of river 1 plus V of river 2 is equal to, they're equal, so the ratio is 1 to 1. Let's call this 2V of individual rivers. So this is basically they're equal, so it makes it a little bit simpler. So in terms of the alkalinity, then it would be 2V equal to, 2V of alkalinity of the mix is equal to V times alkalinity of river 1 plus V times the alkalinity of river 2, or the alkalinity of the mix would be basically the average. minus 3.8 minus plus minus 10 to the minus 4. What is alkalinity of minus? Any idea? Exactly. So it's a wastewater, for example, that has a pH of 3. So we need to add negative acid, which is basically base, to bring pH eventually to 4.5. So we did for alkalinity, and then total CO3 would be the same basically. It would be the total CO3 of the mix would be the weighted average, which in this case is the normal average. Total CO3 of river 1 plus total CO3 of river 2 divided by 2, and when we have the values, it would be 10 to the minus 3 or minus 5 minus 3.77, which would be 9. So the last part is basically looking at the pH, and then we have that alkalinity relationship. Alkalinity is basically equal to alpha 1 plus 2 alpha 2 total CO3 of the mix plus hydroxide minus P minus H plus, which is equal to, we can basically expand the term for the alpha value. And this is basically a sort of a weird one equation, one unknown, certainly non-linear. It's known. The only unknown is basically this H plus term. In lecture 10, we talked about how to construct like Excel spreadsheet, for example, to basically deal with this kind of equation pretty effectively. The right side minus the left side has to be equal to 0. So at some point you see the change in sign, minus to plus or plus to minus, and then you zoom in that range. Eventually you get to the value you're looking for. If we do like solving with Excel spreadsheet, then pH would be roughly 6. So you see that 6 is not necessarily the pH of like any kind of average for the two mixture, the two rivers. One is at pH 4, the other one at 7.5. So if you let it go for a long time, for example, the mixture, what would be the pH? Do you think it's more than 6 or lower than 6? So one of the problems, to give you a hint, one of the problems with climate change, increased concentration of CO2 in the air, is basically ocean acidification, right? So as you go down the road, then the pH would be in equilibrium with CO2, then it goes down. So we'll see that later in the next lecture, and we're going to calculate that. Cool. So we can use also Mintech to calculate alkalinity. In this lecture, we only talked about carbonate alkalinity, but in Mintech, if you can basically define other species. So whatever you have in the system that can be considered as a contribution to alkalinity, or you can basically define what's the total alkalinity by going to parameters and then defining the alkalinity as a parameter. So it's basically you pick the unit, the value, and then later it just calculates what you have to get to that alkalinity. So the alkalinity term would be fixed. So here I'm providing just a quick example of we have a solution that has a pH of 7.7. We do titration in the lab. We see that we need 4.7 milli equivalent per liter to bring down the pH to 4.5. So that means alkalinity is 4.7. And we already know that we have 0.4 millimolar of total CO3. But we don't know how much, So we know what's the total concentration of phosphate in the system, but we don't know what's the total concentration of carbonate in the system. Based on the equations we have in this lecture, we can't solve it because we don't know how to calculate for the contribution of alkalinity of phosphoric acid. We just know it for carbonic acid. But here is the mixture of the two. And we know one of the total concentration. But the good thing is we can use visual minting, and it's pretty accurate in terms of calculating that. So first we need to define alkalinity as a parameter. So it would be 4.7 milli equivalent per liter. Then we come to the main page we basically fix the pH because the pH is fixed at 7.7, so it's a condition. And then we define the total phosphate concentration, which is 4 millimolar. And when we run the system, we see that basically the total CO3 is equal to roughly 4.55 10 to the minus 3 molar. And as you see, the total phosphate is how much we initially added to the system. So now we can look at the total contribution of alkalinity because of carbonic acid. So the total CO3 is 4.55 10 to the minus 3 molar. pH is 7.7. So we can calculate the alkalinity due to CO3 based on the equations we have in this lecture. And that would be 4.39 milliequivalent per liter. So we know what's the total alkalinity, so then we can just see the contributions. So the contributions on alkalinity due to CO3 would be 4.39 over 4.70, which is 0.93. For the phosphate system, this would be 4.70 minus 4.39 divided by 4.70, which is 0.07. So this means 93%, and this means 7%. So as you see, a big contribution is from the carbonate system. One of the reasons is because basically it's 10 times more concentrated, but also it has more contributions to the overall. So this is basically the pH we fix, and this is the total alkalinity. So very useful. I think the alkalinity term is a good way. It's sort of a bridge for the sake of calculation. Also from the conceptually, it's also very important because it's very practical. So when we know about the alkalinity of a system, we know how much it resists to a point that is important to us, which is that 4.5 for the two reasons we mentioned. So to wrap up, we described alkalinity. We looked at the qualitative and quantitative approaches of alkalinity. So we defined that alkalinity to be a resistance. So up to here is basically a buffer to decrease to pH of 4.5. That makes it alkalinity. And we mentioned this pH, total CO3, and alkalinity are related to each other, and we use that basically to calculate or to estimate features of the mixture. So the next lecture would be on gas-liquid equilibrium, a very important lecture. We're basically redefining the system. So up to this point, it was all about closed system. Mass balance was always there. But now we're introducing an open system. So that's something that might leave or be introduced to the system. So the whole different ball game. And that would be the last lecture of chapter 2 also.